So yeah, hi, I'm Tom. I'm one of the senior analysts at the Strush unit. We're based within the Midlands and Lancashire Commissioning Support Unit, um, and we do various kind of analytical projects. If you go to our website, you'll find more about what we're doing currently with the COVID response nationally and locally. And I say the Slack channel is really worth joining. I think they're posting the links in the chat now. And if you're wanting to grab the materials, it's on the NHSR community GitHub page. There's a folder called FP with Per. All these slides are in there along with some code examples. So I suppose the first thing first is, what is the Per package for? And if you go to the Per package website, it gives you this quite nice short and distinct sentence about what it's for, and it's honestly a little bit lacking. You need to know what functional programming is. You do need to have a good notion of what a function is and what a vector is. So I'm going to run through first what functions and vectors are before showing off what we can use Per for. And I suppose it's worth trying to mention a little bit about functional programming and what it is. So there's a good website, Master the JavaScript Industry. So it's obviously about a different programming language, but the concepts are the same. And if you read the first 3 paragraphs, it explains functional programming perfectly for a computer scientist. And you do need to understand what all these terms are. And this website does go on to explain them all. But for today, I'm kind of going to gloss over all of these things, what pure functions actually are and what they're useful for, like avoiding the shared state immutable data side effects. We're not going to cover those kind of things. That could be a more in-depth look at functional programming, but I just want to give you a feel for how the Per package can make some workflow problems much easier to deal with. So first of all, I'm just going to quickly gloss over functions for those of us that haven't created them before. They're pretty easy to create and are. If I want to create a function called myFN, I assign it like any other variable, and I write the keyword function, followed by a set of parentheses, and what looks like a variable, but we call it an argument in a function, and followed by a set of curly brackets, and then some code. And all of that code is going to be executed each time that we run the function, substituting in the variable that we pass in as that argument. So in this case, we do 2 times x. My function 3 returns 6. So the arguments, as I say, they're a bit like variables that we use when we call the function. And you can create a function that has 0 arguments. In this case, function's always going to return 3. Or you can have a function that has 2, 3, 4, 500 arguments. In this case, we give each argument a unique name and specify it like that. Then we simply call them with all those different arguments. In this case, we do 3 and 2, and then do 3 plus 2, 5. Very briefly, you might see sometimes this ... argument in R, and this function is what they call variadic. We can have a variable number of arguments. And this is quite useful if you've got a function that calls another function and you want to pass some other arguments onto that other function. The body of the function, the bit between the curly brackets, can be 1 line, it can be 100 lines. So long as it starts and ends in that bracket, that's going to run in that order from top to bottom. And we put some flow control statements in, so your if statements, your else statements, return. This one will immediately stop execution of the function and return that value. We've got a stop method for saying if there's an error, then stop, return an error. We've got loops, which we'll be going over in a bit more detail later. So you can see some examples of what happens when we pass these different arguments here. When we call 2, it's going into this loop here. When we pass 6, it's kind of getting into this bit here and immediately jumping out before we touch this code. And when we've provided a value that was too big, we've thrown an error. Now, something that can be a little confusing at first is notion of the scope of variables. So in R, when we create a variable, we can use it throughout the program that we're writing. But when we create an argument inside a function, it's only going to exist within that function. So here we've created a variable called x, an argument called x, and a variable inside the function called y. And we can check if these variables exist. And this just returns true and true. But then when we write some code outside of the function, those variables don't exist. So we can't use them outside the function. And this is quite useful because when you're working with the functions, you want that logic to be encapsulated within the function. We don't want that information to be leaking outside. So when we run this function a second time, that variable y is being created afresh each time. You can use variables that have been defined outside of the function though. So in this case, I've created a variable called v, and we write a function that uses a value v, and it updates the value v, and then returns this value of y plus v, y being created up here. We get a value of 13. So we do 2 times x, 3, 6. We take that 8, subtract 1, 7, and we get 13. But what's a little bit unusual about R is the way that it handles these variables. So if we were running this here and we've taken that value of v and subtracted 1 from it, we'd expect that variable to have a value of 7. But as you can see, when I've rerun the variable here, I've got a value of 8. And what is happening in R is it looks at that variable and it sees that we're changing it. So it creates a new version of that variable within the function. Now, it's not usually a good idea, but there is an operator which has 2 of the less than signs followed by the arrow, and that will then update the variable in the global environment. But it's probably best to avoid that. We then also have the option of creating functions with default arguments. So here we say y equals 3, and that allows us to just run the function, my function 4, and it will put in the variable, value of 3 for y. We can then set a value of 5, and it will run it with y equals 5 rather than y equals 3. So that's quite useful if you're building a complex function that has some arguments that usually you have a good default value for. A great example is the mean function in base R, which has the na.rm variable, and that's by default set to false, but you can change it to be true if you want. Now, when we create a function like this one here, the order of the arguments is how we pass them in. So we put 4, and that goes to x, we put 5, that goes to y. But if we want, we can call them in any order. We can say y equals 5, and then we can say x equals 4, and it will run those with variables in that order. You can kind of mix and match, but it's not recommended. So this would first set all of the arguments based on the name that you give them, and then it will run the rest in order. So that's quite confusing and hard to read. So if you're going to name the arguments, it's best to just name them all. Now, this next few parts, this is starting to get into what functional programming is about. But in R, we have our functions and they're assigned just like any other variable. And we can use them just like any other variable. In fact, we can pass a function as an argument to another function. So here I've created a function called average. And what average is going to do is it's going to take some values and a function, and it's going to return the values that we pass against that function. So here I've said we've got some values 1, 2, 5, and 8, and the mean function, and we get 4. Down here we do it instead with the median value, and we get 3.5. So an important thing to note when we're using functions in this way is I haven't put the brackets after mean, or I haven't put the brackets after median. So those brackets are going to cause the function to evaluate against the arguments that we pass. In this case, we are just passing the function as is. So that allows us to move that function between other functions as needed. We'll see this used quite a lot later on. Another little neat trick though, when we type a name of a variable into the console in R, we get the value spat out in, if we have a variable with a value of 3 and we type that value in, we'll see 3. But if you type a function in, you'll see the definition of the function. So this can be quite useful to kind of see what your function that you've built yourself is actually trying to do. You can also use it against built-in functions or functions from other packages. Like in this case, I've typed in mean, and it tells us what this function accepts, those different variables here, the x and the ... But it does something weird called this use method. Now, if you're interested in finding out what this is really object-oriented programming, and it's described in the advanced R book. So you can go through and read about that if you want. This link here is in the slides, takes you straight through to that chapter. And this one is a very kind of weird concept at first, but you can create what's called a function factory. It's a function that returns another function. So in this case, I've created a function called dice. And what this is going to do is we pass in an argument called sides, and it's going to return a die that has that many sides. So I create a 5-sided die, and I can roll it once. This gives me a value of 1. Or I can roll it 10 times. We can see here we've got the values 1, 2, 4, 5, -3 when we run it this time randomly. But that will then be a new function that we can use over and over again. In this case, I create a 12-sided die and roll it 20 times. We get the values like that. Now, this is quite a useful pattern that you'll see in some other functions. For instance, in the scales package, you've got the functions for formatting numbers. And they have the number function, which formats a number. But you also have the number underscore format. And that allows you to set some of the things like the accuracy and things like that, and return another function that then passes the value in and returns it in that format with all of the options that you've already specified. Now, very quickly, functional programming deals with this kind of concept of pure functions. And a pure function is related to a function in mathematics. The basic idea of a pure function is that it's going to have no side effects. And a side effect is where it's going to change the state or use the state from outside of the function. So in this case on the left, we have a value defined in the main environment, the global environment. And our function expects this value to exist. If this value wasn't set, it's going to return an error. Now, when I run this first with a value of 3 and this value of 4 and evaluate it, we get 7. And then we update the value of up to 10, run it again with the same arguments, we get a different value. Now, this can be a problem because if we're writing a function and we're depending on having this value set, that value could change and we might not realize it. It could be something that's built into the computer, that an environment variable, or it could be a value that we're manually having set. But when things start going wrong, it's a lot harder to trace those issues back. So this concept of a pure function doesn't allow us to use this value here. What we would do instead is pass it as another argument. So in this case, I've called it y. And that time we pass in value to that second argument. Now, the results are the same, and you may be thinking, how does that help? But as you start working more with functional programming, it does start to make you think that it's a neater way of working, that we have this guarantee that each time we run the function with the same values, in this case, we change the values so we get different results. But in this case, we ran them with the same values but got different results. It makes it a lot easier to debug some issues that come up. It makes it a lot easier to build unit tests to verify that your code is running in the way that you expect them to. The problem with this is you can't do things like read files in, so all our read TSV functions and reading from a database, writing plots to disk would not work in a pure function. So I'm really not going to cover that kind of element of functional programming today. But if you can think of a function in a pure way, it will make your life easier generally. So next, I'm just going to briefly cover the topic of vectors in R. So vectors are what you're storing all of your data in generally. There are two main types of vectors. The first are the atomic vectors, and these are the base values. You've got your logical true and false values. You've got your integer values, which are the whole numbers. What you have most of the time instead of integers is doubles, so 1, 2, 3, pi. And you've got the character vectors, strings and text. There are other atomic vectors, such as dates and factors, which are built up from some of these base atomic vectors. So a date is just stored as a number from the start of January 1970. But the implementation is hidden from you. Now, the important thing with atomic vectors is they're homogeneous. They can only contain the one type of data. So if we have a logical vector, it will only store true and false values. If we try and combine a logical vector with an integer, it's going to turn those logicals into integers. And if we combine an integer vector with a double, it's going to convert them to doubles. So if we combine those doubles with characters, it's going to change those to be strings. Now, on the other hand, we have lists, and lists are a bit weird at first. A list is also a vector that contains values, but it's heterogeneous. It can store different types of data in. So in this first list, the first thing it's containing is a single double value. Then it's containing a vector of doubles. Then it's containing a character. And then it's containing another list. If we use the structure function, str, we can have a brief look at how that list looks. And we can see that we've got the 1, we've got the 2 and 3, we've got the string there, those different values. And we can also inspect individual elements using the brackets like that. Now, lists are a lot harder to work with in general. They are more complex data structures. So if we can work with vectors where possible, great. Now, a quick thing about these named vectors is, by default, if we just pick a vector like the letters that's built into R, we look at the first 3, that just returns 1, 2, and 3. And we can refer to these letters then by the numerical position. But sometimes it's quite useful to have a name that we can refer to an item in a vector by. So here I'm creating a named vector with the first 3 numbers, 1, 2, and 3. And I'm naming them A, B, and C. And when we inspect in the console this named vector, we see how these line up. A is 1, B is 2, C is 3. And then we can access an item from that vector using the name. We can also set names after a vector has been created. So in this case, we've got the numbers 1, 2, and 3. And I pipe it into this function from Per called setNames. I use A, B, and C as the labels, and it will create that vector for me, just like before. So we'll be using this a bit later on to handle some more complex things in Per, and we'll see how useful these named vectors can be. Using this pattern in particular, if we pass a vector in into set names, it will set the names to be the value. And this looks kind of odd at first why we might do this, but I'll give some good justification for why this might be a useful pattern later. Now, briefly, probably the data type that we use the most in R is going to be a data frame or a tibble. But a data frame under the hood is literally just a list, but with one very specific constraint. Each of the items in the data frame is going to be the same length as every other one. So our columns then refer to items in the list, and the rows refer to the combination of each pair of items throughout those lists. So we can have a quick look at the built-in data iris. And if we run class, we see it's a data frame. But if we run the type of function, it tells us that it's a list. If we run the length function, that's telling us there's 5 items in this list. And we can use the structure to have a look at iris. We can see that these are then 5 items, each of the same length. It's kind of cropped off the screen there, but each of those vectors will be 150 in length. So that's kind of a quick overview of the base level of knowledge that you need to kind of get into Per. So I'm going to briefly go over this notion of iteration. So imagine that we have a series of values. Here I've got the numbers 1, 4, 5, 3, and 2. We can have a look at them. And I've created a simple function here. So my function is going to accept a value called x, and it's going to take that value, multiply it by 3, and then add 2 to it. Now, the cool thing about R, in comparison to a lot of other programming languages, is that it's vectorized throughout. So if I was to run this function here with all of my values, just pass in that vector, it knows to run through that first item, run that second item, run that third item, run that. And it gives us the results that we expect there. We calculated this by hand. Now, occasionally, we'll find functions that aren't vectorized. We can't pass in the variables in that way and expect them to work. So what I'm going to run through next is how we create a loop and do this same kind of thing here, but in a loop. So let's just pretend that we can't pass in vectorized values into R. The first way that we might try to do this is with a for loop. Now, a for loop is, in programming, is saying, go through all of these items and do this evaluation for me. So what I'm first going to do is create a vector called results that's the same length as my values, ready to store the results in. So when I create that, we get 5 values that are all 0. Next, I'm going to set up this loop. So I want to go through the values from 1 up to the length of my values. So we had 5 items in my values. So 1 to 5. And I want to set I equal to 1, 2, 3, 4, and 5 in turn. So then we'd run my function with the ith value from my values and set it to the ith value from the results. And if we do all that and look at the results, we get the same as before. There are some issues with writing loops in this way, though. For one, we could forget to initialize this results, and then when we try and set this, it's going to probably throw an error. Or we could initialize it incorrectly. We could say, I actually want a numeric of 3, and then we won't be able to store the 4th and the 5th results. Or I could say, I want a numeric of length 10,000 and use up all the memory in our computer. So we need to be careful on setting that vector up correctly there. And then setting up this loop, we can make mistakes here. If I put 2 there, it's only going to go 2, 3, 4, 5. Or if I put the wrong variable in here and iterate over a much larger vector, we're going to try and access values that don't exist. And a very common one that I've done too many times to count in the past is start writing some code to test this out. And instead of putting I, I'll put 1 in. And I'll run it and test it. It works with the first value and go, great. And then I'll update my loop and create this. And I'll have forgot to change that to the variable. So we end up with 5, 5, 5, 5, 5. So the question is, can we do this in a better way? And Per gives us the solution to that with the map function. So map basically does all of that stuff for us. What map does is it accepts a vector as input and a function. And what it's going to do is it's going to run that function. So in this image here, f with the first value, f with the second value, f with the third value, and f with the fourth value. So running this with my values and my function, we can see we get the same results: 5, 14, 17, 11, and 8. But the key node amongst you might notice that this has returned a list for us and not a nice vector. And that's because map always returns a list. And I kind of touched on earlier, lists are much harder to work on. So I took the values before into a variable called results. And if I try and work out the mean of those results, it tells me this really weird message that argument is not numerical logical, and it returns an A. So can we do better than that? And fortunately, PER does help us out here. So when we looked at those vector types earlier on, we have corresponding functions from PER for those. So if we have a function that returns a logical, we can use the map LGL function. If we have a function that returns an integer, we can use that, so on and so forth. Now, these work if the function that you use back here, so if I just scroll back up, if this function returns a single value, then we can use those nice little helper functions. So in the previous example, we have map unscudable, my value is my function, and we get the results that we're expecting. So that's a very brief look at map, but when we've got a function that's vectorized, it doesn't make much sense to be going through all of this effort and using this. We can just run my function with my values. So we'll come to a more practical example in a second. Briefly, I just want to show you how you can also pass in your functions to map. So in the previous example, we just passed in a name of a function that we created. But if that function is only ever going to be used in that map statement, we can create what's called an anonymous function. So this is just a function that hasn't been given a formal name that we can use elsewhere. We're only using this function in the map. We just define it straight like that. So we just write function, we don't bother assigning it to a variable. And PER will know to take my values and run it against this function each time. And we get the same results. But PER also provides this really neat and concise way of writing these kind of anonymous functions out. So if you just write the little tilde or squiggly kind of character, you can say the same kind of thing there, except it calls the .x as the argument. And we'll run that and we get the same results. So very kind of quickly, why would we prefer this over that? I would argue use the formula syntax if your function is like really simple. If it's one line, do it with that kind of squiggle syntax formula. If your function's got 2 or 3, 4 or 5 lines, it's not kind of going off onto multiple pages, then this anonymous syntax works really well. And if your function's far more complex, or perhaps using it multiple times in different parts of your code, then define the function outside of the map statement and use it that way. Now, one of the other neat things about map is every other argument after the vector of input and the function is passed to the function at each evaluation. So in this image that's been borrowed from the advanced R book, you can see that we iterate over these values, but we pass the blue values to each function call. So let's imagine that we took that function that we used before, but instead of saying +2 every time, we add it as an extra argument. Then we can run map function here like that, and just passing that variable of y as 2. Now, good practice here would be to name that argument so it's a lot more clear what it is that we're passing in. And that's particularly true when you've got functions that have default arguments that you're passing in. Now, very briefly, I think a quite cool way of using the map is with data frames. So if we remember, I mentioned before that a data frame can be thought of a list where each of the items in the list is a column in the data frame. We can use map then to iterate over each of those columns of data, taking in all of the value at once and run some function against them. So if we look at what the iris dataset looks like, if you've never looked at it before, we've got 4 columns that are numbers, 1 column that's a factor. And if we run the map underscore check character function on the iris dataset and run the class function, it tells us that that's a numeric, that's a numeric, that's a numeric, that's a numeric, and that's a factor. Comparing it to just running the class function on the data frame, and it just says it's a data frame. This can be a way of getting far more valuable information out off that data set. Another way of using this would be to say, go over each of the columns and get the unique list of values from that column. And then we can pass that vector into the map double function and work out the length of that unique list. So this is telling us how many unique values are in each of those columns. So this is another one of the kind of concepts of functional programming that I'm not really giving much justification to today, but we're able to compose functions together so we can achieve a more complex result by running multiple things in sequence. Now, the clever amongst us will probably think, well, I could just use the summarize all function with end distinct and get exactly the same results. And in fact, this way is better because I could use the group by and get perhaps the unique number of values per each of the species. And yeah, of course, you could. There's many ways to skin a cat in R, as in any programming language. But what I kind of wanted to say on that front is map is a really generalized way of solving these problems. It's a great kind of Swiss Army knife that you can use to solve a lot of problems that would require you to know all these clever functions and tricks maybe, and solves them in a way that's a lot easier for you to understand. Another way of using map though is within a data frame, I'm going to call this. And I'm sure that we've used the mutate statement before with a function to work something out. But imagine here, I've got a tibble where I'm just listing the files in this folder, and we have these 2 files, map.arg recycle and map.png. So those were those 2 images that I borrowed from the Advanced R book. And we wanted to work out how big those files are. So within this here, I'm creating a new column called file size. I'm mapping over the files column, and then I'm running the file size function to create a new column with the size of each file in. So, do we have any questions on Anastasia or Anastasia before we continue?
Yes, we had one about map, and someone's asked if map works with charts as the output of a function.
Yes, so I'll be kind of covering that a little bit later. So pretty much in R, everything that you're running is a function. So where we're creating a function, well, using the ggplot function, we could of course iterate over some data and use the ggplot function as a target function to generate those plots. So yeah, I'll be coming on to that shortly. So yeah, I'm going to go over a bit more of a practical example of using the map function now. So far we've kind of looked at a lot of things that could have been achieved easily with just using a vectorized function. But a really common pattern is that we have a folder full of CSV files. So in this case, within this project, there's a folder called A&E Attendances, and there are 36 CSV files corresponding to the 4-hour performance data from 2016 through 2019. So I'm just using the dir function here to get a vector of files. This weird looking thing is just called regular expression. So it's just looking for the files that match 4 numbers, followed by 2 numbers, followed by 2 numbers, followed by .csv, all separated by hyphens. Now, that has just produced up these here. These are the first 10. And what happens if I want to just run the read TSV function to read in these files? So if I call read TSV with that files vector, I get a very weird looking tibble full of 35 rows of data with a column called the first file name. And I don't think that was the results I was hoping for. So instead, we could use map to iterate over all of those files and call the read CSV function on each of those individual files. And if you remember before, map returns a list always, so it's cropped off the screen, but here we have 36 different tibbles returned from the read CSV function. Very quickly, I've thrown in the column types that are being read in each time, and this is really good practice with the read CSV function. It ensures that we're always going to be reading in the files consistently, and it also gets rid of some really annoying error messages, well, warning messages, sorry, that come up each time we load the file. Now, that's great that we've managed to load the files in, but it'd be more useful, instead of having this as a list, to have it as one single data frame. And Perl has us covered on that front too. So there are these map_df functions, and there's actually 3 of them. There's map_df, which is, I think that's been deprecated. But then there's dfr and dfc. And the difference between the two is dfr is for rows, dfc is for columns. Now, the one that I've never had a good use case for dfc. I'm always using dfr. And you can think of this as running a function and then doing a union all from SQL on that result. So in this case, I've run the files, called the read CSV function, and return it as a data frame. And now we have one single data frame with 12,000 rows of data. So if we have a look at this, there's something that is missing from this data. And it's something that's quite important, I think. We don't have a way of distinguishing any of these rows by the date that they happened. Now, if we looked at the files, they don't have the date column in, but the date is listed within the file name. So each of these files refer to an individual month's worth of data. But the map_dfr function has a really neat trick up its sleeves. And it's this .id argument. And what that does is it will take the name of the vector and it will add it as a column to your data frame. So this is where that pattern of using that set names function that I mentioned earlier comes in. So here we take that files, set the names, and it gives each item in the vector the name of that file. So that's looking at the first 3 items. And what we can do now is we can do map_dfr with the ID into a column called file name. And it set that file name against each row of data. I've also added in a little thing here to kind of pull out the date. I've put a little explanation there to what that's actually doing. This is also built on R version 4, so this syntax is just a bit of a neat way of writing regular expressions in R4. If you haven't upgraded yet, get rid of the R at the start and then just replace all the slashes with 2 slashes. So that's kind of a brief overview of the map function, but there are a fair few more variants on this. For one, if we have 2 vectors that we want to iterate over, there's the map_to function. That you need a function that has a .x and a .y variable. So here you can see we've created a little function that's just going to take .x and .y and multiply them together. Then we iterate with the numbers 1, 2, and 3, and 4, 5, and 6. And that's going to run this function here with 1 and 4, 2 and 5, 3 and 6, and gives us those results. And the map2 function has all of those same kind of underscored variants that we saw with map. And there's also pmap, which is a generalization of the map and map2 functions that works when you have like maybe 4 or 5 vectors of the same length that you want to iterate over. So it's a little bit more confusing to work with, but you shove all of your vectors that you want to iterate over into a list. And then you'd create a function, in this case, x, y, and z, that's going to take x multiplied by y plus z. So like before, if we took that result and added 7 to it, so on and so forth. Very briefly as well, that the way that this kind of works is if you use a named vector, it's going to match the arguments up against the function name. So in this case, I've got a function that's called accepting C, B, and A. It's running it in the reverse order to what we saw before. But because we've used a named vector, it knows how to match those up. So this is really useful when you're working with a data frame, because we'd have a function that has the names of all the columns. And quickly, walk is similar to map, except it's designed for functions that you just want to run solely for the side effect. So things like saving a file to disk. So I'm going to show that off in a second in a brief demo. So Alessia, do you have any more questions before we continue?
We have one from Jamie. So yeah, it might was answering now because it's about your Iris example. So Jamie asked if using mapply gives you any advantages over using map. And also there is example of code in questions. Map worth checking rather than me reading by its Iris and then pipe operator, mapply unique, pipe operator, mapply length.
Very briefly, let me just go see if I can go back to my slides. I have got the most briefest thing there. Yeah, there is almost no difference to using the map functions versus the apply family of functions in base R. The reason why I think the map functions are far better than those is if you use apply, you've got this weird argument that's called margin, and it takes a value of 1 or 2, and you need to remember whether it's a 1 or a 2, whether you're going over rows or columns. And you've then got sapply, which is meant to be like simplify apply, which will return a vector that it thinks is appropriate, but sometimes it'll just return the list. And then you've got vapply, which I've never been able to figure out how to use that properly. So yeah, I mean, if you're comfortable using the apply family of functions, carry on using them. The perf functions are a lot easier to work with. The documentation's a lot better. And I think, as you've kind of pointed out there, Jamie, the mapply functions have the function and then the data first, so they don't work so well with the pipe operator. Do we have any other questions, Alessia or Anastasia?
So we've got one here asking, what are the best methods for flattening lists, converting to atomic vectors or data frames?
Okay, so per, I'm covering so little of per today. I'm like barely scratching the surface, but there are some functions in there. Let me just make sure I'm on that. There are the flatten family, and you've got all of those same kind of variants that we saw before. So you can have something like this: A, B, C, E, D, maybe like that, and then you've got and I've made a mistake there because I think this is, yeah, you need to wrap those in lists themselves. Trying to work this out on the fly. Sorry. yeah, so that first flattens this weird nested list, and then we could flatten that secondly. So that's how you would be working with kind of really complex data sets that are built of weird nested lists. Hopefully that answers your question. But if we don't have many more questions right now, I can just run over this demo and come back to more questions later.
There was just one more question, Tom, but it's up to you whether you want to do that afterwards or now. It was just asking if it was possible to use map to iteratively map to its own outputs. For example,
yeah,
output of a map into a new one.
Yeah, so we could do something really done quickly here. So we could do map, and we can do maybe .x times 2, and that's going to give us that list like that. And then we could pass it into, say, map double, and we could do .x plus. And you can chain these up as much as you want. You can have map after map after map after map. You can compose them kind of infinitely. But yeah, anyway, I'm going to run through very briefly a quick demo of working with Per here. So let me just get my crib sheet up. So what we have here is the A&E attendances data. And of course, I forgot to include the package here. So NHSR datasets is a package that we've been developing. And one of the datasets there is the A&E attendances that we saw before, except this time with the date included. Anyone that works with kind of NHS data knows that, or hopefully knows, that organisations that are kind of provider trusts start with NR, and we can kind of see here there's some data for some of these kind of private providers that are doing these urgent care centres. So I'm just going to try and filter these out. So I'm going to take the all code column, pass it into the starts function, and I'm going to say it starts with an R. So that's given us a nice little data set now, filters. But we can see that this data is, we've got these different kind of rows for all the different types. I'm just going to compress that quickly. Now, what I'm hoping to do with all of this is produce a plot for each organisation, for each showing, month by month how the attendances have changed. So if I start off with this, then filter and.
Sorry, Tom, just distract you for a second. Is it possible to zoom in at all?
Yeah, let's do. Let's just try to remember which way. So I'm going to try and zoom source quickly.
Brilliant, thank you.
Yeah. So, yeah, we can do kind of basic kind of dplyr working here of grouping by this, and then we could summarize the attendances. We could say some attendances, but dplyr has some kind of functional concepts, like functional programming concepts itself, and one of them is summarize at function, and in that you can pass in a name of a column and then just write the function like that, which I think is a lot neater. We're not having to write out the function, column names over and over again. If we run that, we get the same results as we'd expect if we had run them kind of individually. But what we should note is we've still got the groups on that data there. So if we have a look at groups, last value, it should tell us that we're grouped by all code. Now, let me just keep copying and pasting this. One cool thing in dplyr that you may have seen before, or probably not, is this kind of notion of a nested data frame. So here we've got three columns: the org code, the date, and the attendances. And this org code is repeated multiple times. But if we nest the data, we should see now that each organization has one row, but it has this kind of nested tibble. And this can be really useful for some of these tricks of like producing multiple plots. Now, we'll also see here though that some of these organizations don't have the 3 years full of data. So what I'm going to do quickly here is I'm going to take that data column with map, and I'm going to run the nRow function and check that it's equal to 36. So we've seen kind of already today how we can use the map function. And just as a justification of why we'd want to do it like this, just copy and paste this. We just ran on that data. Let's run this. We're going to get a really weird error message. The results must have length 1, not 0. And that's where using map really comes into its own. We can calculate far more complex things by mapping over and evaluating some function than if we just try to run the naive approach. Now, kind of the difficulty of using this nested data frame, if I run that, we'll see we've got this just like weird little kind of tibble. It doesn't tell us much about it. So what I'm going to quickly do is have a look at the last value of data. All that back up here, and we can see that we're expecting a column called periods and attendances. So I'm going to create a function. So that function is going to take in the org code, because that's what the original nested column was called, and the other column was called data. I'm going to take data, pass it to ggplot, and I'm going to use the periods and the attendances column. It's something really plain and vanilla, but you'll get the point across. And I'm going to add in a title and use that org code argument that we passed in here. So that's created a nice little function for us. What I'm now going to do is I'm going to take that data that we're using here like that, with the org codes and data, and I'm going to create a column called plot. And this might seem as a bit of a weird concept of creating a column in a data frame with the plot, but it's going to kind of work here for this purpose. So in this, I'm going to go map2. So this is that function that works with two vectors that we're iterating over. I'm going to take the data column, and then I'm going to use that plot function. So that's created that extra column for us. Now, just in the interest of time, I'm going to kind of gloss over this. There is the whole demo is in the repository, but what we can do with this is I'm going to also create another column called file name, and I'm going to go personal a plots, and I'm going to use the org code column and call it .png. So that's going to create this for us. Quickly, I'm going to create a new folder to store this data in. And now what we can do is we just rerun that and have a look. If I get rid of this org code and the data column quickly, which would leave us with just those two columns. And of course, I'm getting bitten by forgetting to ungroup my data. Run that again. So we've got a column called file name and plot. I'm then able to iterate over that data with the plwalk function and use ggsave And if you look at the arguments for ggSave, it takes a file name and a plot, and it's going to save the file to that file name there. So let me just try and bring back up. Focus source. There you go. If we run this, I'm just going to run it over 10 of those items. You'll see it's saving 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And hopefully, if we look in the A&E plots folder, we should see those files have been created. And let me just quickly bring up everything here and go into that folder. And we should see one of the plots has been created. And that's a very brief overview of how you can use all the combination of map, walk, and some built-in functions in R as well as your own functions to do something a lot more complicated than you could hope to normally do, generating multiple files. I've got another version of this kind of demo here that's running through rendering multiple R Markdown reports. So I'm using it here to generate a report for 5 different organizations. But that's pretty much it.